People, this is lecture 15 on March 2nd, 2023. And on the agenda today, we have the concept of impulse response of functions. Uh, Actually, I uh, better put impulse response function. Okay. So let me tell you what the story is. The first 3 weeks of the course, we looked at the free vibration of a mass spring damper system, a single degree of freedom system. And now, obviously, this could have been translational, this could have been rotational, this could have been a very complicated problem that you idealized it as a single degree of freedom system, and it really boils down to the mother of all equations, which is mx double dot plus cx dot plus kx equal to first 3 weeks equal to 0. Okay. Now, remember, x, we look at it as a translation displacement, but it could be rotation, and therefore don't get hung up on the fact that we are only looking at translational displacement of a block, for example. In any event, first 3 weeks equal to 0. The next 3 weeks, we said, okay, it's a force vibration, but the right-hand side is a very special type of a function. It's a harmonic or what is called also sinusoidal. So it can be a number times cosine of, let's say, omega t, or a number times sine of omega t, etc. We spent 3 weeks on looking at these type of problems, the solution, some modifications to it in the sense that it came from maybe displacement of a base, maybe it came from a rotational balance, etc. So what we do today is look at the right-hand side being a very special type, namely an impulse function. In the nutshell, an impulse function is a function that is uh, applying in a very, very short period. Okay, so in the nutshell, that's what an impulse is. And we want to see, first of all, what is the effect of having a force like that acting on the mass in a very, very, very short period, and uh, how do we solve that equation? Okay, so a very common source of vibration is sudden application of a short duration force. That's exactly what I was talking about. A very short duration force applied on a block. And that kind of a function is called an impulse function. Now, in principle, we want to say that this duration of the application of the load is actually zero. I mean, it can never be zero, but we can think about it at the limit of the duration of the application of the force going to zero. And this obviously is something that is a very weird function. How can it be a function and then it basically operates under no uh, time interval? That's a strange looking function, and in fact it is. And sometimes, by the way, they call this thing a shock loading too. But anyway, we go with the concept of impulse function. Okay. Now, uh, it's ironic, but what happens is that if you apply an extremely time duration force to the block, essentially well, think about it as hitting a block with a hammer. Okay, so essentially, all it does is that impact, the impact of the hammer with the block, gives this block an initial velocity, and that's exactly what happens with impulse functions. The effect of an impulse function is really changing the initial velocity from 0 to something else, or from some other value if it already has an initial velocity. If the block, for example, is moving, a mass spring damper system is moving at a particular time in time, there is an initial velocity, there is a velocity of that block. If you hit it with a hammer, so it adds to that essentially velocity that you had, the block had, something else that comes from the impulse. So generally speaking, when people talk about impulse function, they think about it as being applied at a particular time. Let's call this thing tau, time tau. Incidentally, tau can be zero or it can be some other, value. For example, the example that I gave you, a block which is already under oscillation, hit with a hammer, you may want to think about tau being the instant that that hammer hit the block when the block was moving, for example, in any event. So we're going to look at the function that is defined at uh, tau, okay, with a small neighborhood around it. So let's call this interval is 2 epsilon. You can see that. And let's think about the height of this function being f hat divided by 2 epsilon, okay? So an impulse function to begin with, we can think about it like that. And notice that if you look at the area of this curve, the height times the base, it's a number. It's a constant number, f hat. Now what happens, think about it, as epsilon goes to 0. This becomes higher and higher and higher. And in the limit, when epsilon goes to 0, essentially shoots to infinity. But it always has that area underneath it, if you can actually make sense out of it, as being f hat. The function can be written like that. You can see this. This is exactly what we have here. So it's 0 outside of these two intervals, these two time points. T plus epsilon to the right of it is 0. T minus epsilon to the left of it is 0. And it's only alive in this short interval, assuming that epsilon goes to 0 or get very small. So the area under that force function, this is a very weird force function. It's a simple one, but it's a very weird one the way it's defined. The area under that force function is essentially it's the area of that rectangle, vertical rectangle, which is going to be f hat. Okay? Notice that this f hat, this I, or f hat, notice that it says I is equal to f hat. So when we talk about I, you can also think about it as the value f hat. The unit of this is Newton times second. So because we're integrating Newton's force, and there's a dt here, Newton second. Okay. This is written again for your convenience. So I, the impulse, due to this function, is integral from minus infinity to infinity. Basically, impulse is the area under that curve. You can see that. And we just saw that it is the same as f hat. And in the limit, as epsilon goes to 0, essentially that rectangle becomes infinitely long strip with a almost 0 or 0 width. Okay. Now, uh, by the way, the impulse due to any other function, for example, if you have some other function, just hypothetically a function that's defined between, I don't know, -5 and 7, some weird function in between. So the impulse due to it is again minus infinity to infinity f of t dt, whatever f of t is. In this case, it was a rectangle, that's rectangular height. Okay? But in general, it can be some function, and it may be dead beyond a certain point or before a certain point. You always integrate from minus infinity to infinity, but it only has an effect if uh, uh, it's not 0 obviously in those intervals. So it's going to be maybe from -7 to 5 of the function f of t, whatever it is, dt. That's called the impulse due to that force. Okay, here it just happened that our function is a very special type, that's vertical strip, and therefore we're interested in those kind of functions. But in general, the impulse does not have to be because of an impulsive force. It can be any function defined. You integrate it from minus to infinity. If you get a constant value, you say that the impulse due to that function is whatever you got. Here, it's a constant value, and it's the height of that strip. Okay, now it has two properties. First of all, notice that this function, just look at the graph of that function, is uh, as long as t is not the same as tau in the limit. Now remember, in the limit, as long as when epsilon goes to zero, in the limit, if t is not the same as tau, the function is dead. It's zero. Only at t equal to tau, there is a value for the function such that the integral of that weird function that we're talking about is called f hat. It's a constant. It could f hat can be 1, it can be 2, it can be -3, etc. The point is that it's a function that's zero everywhere except for that one point, but it has an integral, and the integral of it we call f hat. It's a very strange function. Yeah, in fact, it is. It's not a regular function. This f of t is not a regular function. This impulse function is not a regular function. So essentially, it looks like that. So we have at the point 0, if you look at the impulse function centered at t equal to 0, it has a height there which goes all the way to infinity, but the area underneath this is a constant, and the constant value is 1. This is how it's drawn, okay? This does not serve justice because the function delta of t does not have a value 1, essentially because the, it's some abstract idea that we're talking about. Imagine that there is this rectangle sitting here that is height multiplied by the base gives you 1, and you let the base go to 0, this area becomes 1. We still draw it like that, okay? So, yeah. This is called, if this area underneath that weird function is 1, it's called the Dirac delta function, okay? And Dirac was a famous mathematician, which I think he was around. He was around maybe 80 years ago, something like that. So a lot of development about this function, which is extremely important in engineering, and it's not a regular function. Mathematicians hate this because this is really not a regular function. How can the function be zero everywhere and it has a height, goes to infinity, and then the area underneath that curve is going to be 1? This just doesn't make sense. So now, if you go back to your dynamics course, you did the impulse and momentum concept there for the first time. So imagine that uh, ball coming in, bowling ball coming in, hitting these pins, and as a system, when you think about it, there is no external force. Now, it is true that there are forces in the vertical direction, but let's not worry about that right now. There is no other external force. So, as a system, the pins and the bowling ball, the momentum of the ball before the strike takes place remains as the sum of the momentums of all of these pieces after the strike takes place. If there are no external forces, and there is none here, okay? If it's bothering you, imagine that this bowling ball was actually in the outer space, okay? And then there is no gravity, there is no weight, etc. So you can still have a bowling alley and roll the ball, and this is what happens. Now, here's another situation. Imagine that we have a hammer, and this hammer is hitting the block that you see there. Okay. Now, notice that when you look at the hammer, the block, for example, the velocity of the block before the hammer hit it, which we call it 0 minus, is 0, and the position of it, we're assuming this is equilibrium, so this is both 0. Okay. Now, when we hit this thing with a force, notice that when you hit the hammer hits this mass with some kind of an impulsive force, the change in momentum, uh, if you look at the change in momentum is mass times velocity, right? Mass times velocity is what is called the momentum. So mass times the velocity of the block after the hammer hits it, immediately after the hammer hits it, minus uh, uh, momentum of the block before the hammer hits it, because this is zero, is equal to uh, uh, you just look at this. Just look at this, okay? Uh, this is the momentum after the hammer hits it. This is the momentum before the hammer hits it. This guy is zero. We already know that. And let's call this thing velocity v dot v naught. Okay, so x dot zero plus. Let's call it v naught, initial velocity of the block. Now, don't be confused. This is not saying anything about momentum conservation. So this is the change in momentum. Momentum after the hit minus the momentum before the hit, except that this one is zero. I know that. And this one I decide to write it as mv naught. Now, this change in momentum in your dynamics course, you were told that the change in momentum is not zero, it's not zero, it is equal to the impulse, which means the integral of the force dt, the impulse apply apply to the block. Okay, so uh, momentum after the hit minus the momentum before the hit, we're talking about momentum of the block, is equal to the integral of the force applied by the hammer to the block during this extremely short time interval. And this is exactly what we call F hat, okay? Because remember, this can be thought of as an extremely short duration event, essentially thinking about that diagram that we had in slide 2, where we had the rectangular strip with a height of f hat divided by 2 epsilon, and the base was 2 epsilon, and the product of it, or the product is going to give you f hat, which is the area under the curve, which is the impulse. So there we are. Now, the change in momentum equal to the impulse, okay? Impulse, that was done in dynamics. And let's think about it. These must be the same. This is the impulse momentum equation. Impulse momentum equation, which is change in momentum, equal to the impulse. That's why we call it impulse momentum equation. These must be the same. And if these are the same, just solve for V naught. Just solve for V naught. Out of this expression, you get V naught equal to F hat. This is the impulse, whatever the value is. It has a unit of Newton second. You see that? Newton second divided by the mass. Okay. So think about it. All this sudden hit does is that it gives this guy an initial velocity. And what is that velocity? You have to know the mass of the block. You have to know the magnitude of the force applied by the hammer to the block, and you have to know the time interval during which it happened. Okay, so if you know these two somehow, then you have the product of them is what we call f hat, and we can actually solve for the initial velocity. Okay, now hence an impulse applied to a single degree of freedom spring mass damper system is the same as applying an initial condition of initially no displacement, but an initial velocity which comes from that expression. So what I just read to you is precisely what it's saying here. Okay, so let's see now. Suppose that f of t is a general force. I mean, in a second, I'm going to change that to an impulsive force. But suppose that you're looking at the general arbitrary f of t. So here's the mother of all equations: initial conditions, initial velocity. Notice that this thing can be written. This thing can be written, if you divide by m, can be written as x double dot, and c divided by m, you can show that it's this 2 psi omega n x dot plus omega n squared. You can see that k over m is omega n squared, equal to big F of t divided by little m, the mass, which our author calls it little f of t. Now, if this is an impulsive force, if this is an extremely short duration, when I say extremely short duration, it means the limit, we're talking about the limit of that duration goes to 0, this is 0, because nothing happens after that short duration. There's no force. Let's assume that the initial position is 0, and we just found out that this velocity, initial velocity that's imparted because of that sudden hit, is actually f hat over m. Okay? So if f of t is an impulsive force, is an impulse, this is what we got. A homogeneous equation. So essentially it's a free vibration subject to initial displacement, whatever it is, and initial velocity. In that initial velocity, you have the magnitude of the impulsive force. Shows up. That impulse shows up. It appears in the velocity expression. Now, we spent 2 weeks. The first 3 weeks of the course was actually solving equations like this, where the right-hand side was 0. Right-hand side is 0. And in 3 weeks we spent on this, we came up with a solution. Remember here, this is the amplitude that we had called big A. In it there is velocity, initial position, initial displacement. Okay. Or if it happens to be 0, of course, no problem. Just this is 0. F naught is not 0. It's definitely f hat over m. Okay. And then there is this angle phi that we did this thing. We did this thing in the first 3 weeks of the course. It's not going to go away. Okay. Now, in the event that we assume that initial displacement is 0, so it starts from equilibrium position, and of course we applied an impulse. In the event that this happens, 0 initial displacement, but of course it's not going to be 0 initial velocity because we hit it with a hammer. So it's going to be change. There's going to be a v naught that is alive. It's not 0 anymore. It's f hat over m. Remember, the harder you hit it, the bigger the f hat, the bigger that interval, the harder you hit it, is the taller that force curve, and bigger the velocity. That's obvious, common sense. Now, we solved this equation. This equation, the equation, mother of all equation, equal to 0 with these two conditions. I just showed it to you on the previous slide, slide number 6. If you plug these these values, this is what you're going to get. For an underdamped, I on purpose I made this thing red because some people read this thing if they're in a rush. They say, "Oh, for an undamped system." No, 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 no. Underdamped system. So underdamped means there is zeta involved here. There is uh, what is called damping ratio involved. There is damping frequency involved. Okay, of course, there's also a natural frequency involved there. So now this is so important. This combination, you see that this combination E hat divided by m omega d sine of omega d hat is so important that people give this thing a name. This is right there. This is right there without the f hat. This they call it impulse response function. h of t. Notice that this response of the system due to the hit with a hammer, an impulsive force, is written as impulse response function times an f hat right there. This is the response of the system. The response means the motion of the block in terms of the impulse function, and this is called the unit. Uh, this is called the response of an response uh, function or impulse response function, impulse response function. But because there is a 1 here, it's due to a response due to a unit impulse function. In other words, when you apply that delta t, area under it is 1. So if you apply that delta t, the right-hand side of the equation is your delta t, then this is the solution, okay? If the right-hand side is not delta t, maybe it's 5 delta t, for example, then f hat is 5. So f hat is actually that area under the curve. If the area under the curve is 1, this is called the impulse response function, okay? And of course, it's due to the unit impulse. Okay, so let me write this thing again. H of t is the response function due to a unit impulse, in other words, delta tau. Now, t may, if t, if a tau, if tau is 0, obviously this is centered at t equal to 0, right? But it may not be here, maybe over there, it doesn't matter. But right now, the way I've drawn it is that this is impulse function, which means delta function, at t equal to 0 or tau equal to 0. And this is the solution to that equation. When I say to that equation, is the mother of all equation, mx double dot plus cx dot plus kx equal to delta t. Okay, delta t. It's right there. This is a solution. Now, in the event that your delta function or the response is at a different time instant, then this is shifted to the right. And we know when you shift things to the right by amount tau, then you just write it at delta of t minus tau. Okay? Now, let me just back up for a second. For example, suppose that we have a block, mass spring damper system, block that's oscillating back and forth. Okay? Then you hit it with a hammer. After 5 seconds, you hit it with a hammer. So obviously that impulse is not at time t equal to 0 because you hit that was already moving around, okay? You hit it after 5 seconds. Then that is an impulse that is not at t equal to 0, it's at a different time. Now, so the solution to this equation, when delta is not centered at 0, it's at there, it's going to be exactly the same thing that you have up here, except that every t is replaced by t minus tau. So basically, it's a shifted version of that, okay? Or a delayed version by tau seconds. So there we are, okay? Now notice it says for t bigger than tau, because for t less than tau, you know what? Nothing was happening. There was nothing hitting that block. But for t after bigger than tau, then there's the solution. You take the h of t, you replace every t with t minus tau, and just write it again. And these are called impulse response functions of the system. We already know that. I already said that. H of t is the impulse response of the function. And we don't say unit impulse response because already there is a 1 here. We already put a 1 here, essentially. Your f hat is here. You look at this. F hat is 1. That's why I put a 1 here. And this is called sometimes unit impulse response response function, but I'll leave it like this, impulse response function, okay? And in the event that the impulse is applied at a different time, then we just shift everything by tau. There are some comments that I want to make about this h of t. This h of t is so important in what we're going to be doing that it requires some thoughts. First of all, it's an excellent model for a force applied over a short duration period. Remember, this h of t is nothing but that strip, rectangular strip, with 2 epsilon, height f over 2 epsilon, however, or f hat over 2 epsilon. However, we are thinking about the limit as epsilon goes to 0. So think about that rectangle. When the width of it goes to 0, the height of it keeps going up, but the area underneath it is still that f hat. So it's an excellent model for force applied over a short period of time. The only thing impulse does, when you apply an impulse to a system, the only thing that it does, okay, is to produce some initial velocity, okay, initial velocity, or changes the initial velocity. If the initial velocity was 0, it introduces initial velocity, and we just found out what it was, f hat over m, okay, and we'll see what happened. It already has a velocity, and you hit it with something, and of course you have to add something to whatever you had before. So we will see that. Now you might say, okay, but not everything we're hitting with a hammer. What if that force that we apply is not actually impulse, it's some arbitrary force? I will show you that if it's an arbitrary force, not an impulse, you can always represent that by a series of impulses. That's kind of hard to see, but believe me, there is a reason that we are doing this, because remember I said that we want to be able to solve the mother of all equations, mx double dot plus cx dot plus kx equal to f of t, where f of t, big F of t, where big F of t can be anything. Okay? So it may not be an impulse. Right now, the last half an hour, we assume that this f of t has a very special kind, that strip basically, it's a delta function. But if it's not, I'll show you that it can actually be represented by a lot of impulses. Hard to believe, but that's what it is. Uh, this happens, this impulse function that we are talking about, this delta t, which leads into h of t, this impulsive function or impulse, that is that strip shooting to infinity, area underneath equal to 1, which is delta t, uh, is very common when you were thinking about impact. Hit it with a hammer. That's very close to what we were discussing a minute ago. Now, in testing mechanical device under test, usually we hit it with a hammer. That's an instrumented hammer, okay, hammer test. So that hammer not only imparts, an impulse to the block, but it also measures internally that, think about it as F hat, okay, or F. It measures the magnitude of that force. That's the role of a hammer. Now, this is a loaded issue. In other words, I say that if the duration of the application of the load is very small, so when you actually hit a block with a hammer, that duration is not 0. It's very small, of the order of millisecond. Just visualize it. You hit it with a hammer, the hammer is in contact with the block for a duration of time. That duration of time is not 0. It's some finite, very small number. The question is very small with respect to what? Is 10 to the minus 20 small? Well, not if you're comparing a 10 to the minus 40. Not if you're comparing it 10 to the minus 60. It is 10 to the minus 20 is small compared to 10 to the minus 10 or compared to 0.1. So this is a loaded question. We are using this thing in a very loose way. The idea is that it's small compared to the natural period of the system. Remember, that system, it has a natural frequency, square root of k over m, omega n square root of k over m. That's the natural frequency of vibration of that object. If you take 2 pi over it, you get the period of oscillation of that object. Okay? Let's pretend that there's no damping there. Okay? So when we say small, if this is small compared to that, for example, if the natural frequency of vibration is hypothetically a natural period of vibration hypothetically is, I don't know, maybe 1 second or 0.1 second. Yes, 0.001 is compared to 1 second or 0.1 second. So remember, small delta t duration when you compare it with the natural period of oscillation. Again, I'm not saying how much smaller. Is it a factor of 1,000, 10,000? No. So, but just remember this small compared to that. Typically in vibration tests, now remember we are also working with real life situation. If you take a hammer, hit a block with it. Hey, listen, uh, that duration on which the hammer has been in contact with the block is not 10 to the minus 10. I mean, you can actually measure it. That instrument hammer does that. It's of the order of milliseconds. Okay, so we are used to taking stuff like this and say, oh, if the force applies over that period of time, we're going to treat it as an impulse function. Okay, I'll take a break and I'll do this example in a minute. Okay, this is the first example we're going to do. We have a mass spring damper system, and we hit it sitting at the rest condition. Okay, we hit it with a uh, instrumented hammer, and some information is given here so that it actually produces that much impulse. In other words, when you hit it, the hammer tells us that the amount of impulse was zero point 0.2 newtons times second, or newton second. Okay. Now, uh, but uh, so first of all, if we hit it once, then that f of t is essentially the first term here. Okay, we hit it once at time t equal to 0, and you get zero point 0.2 delta t. Now, very often you hit it one more time after so many seconds, after tau equal to half a second, 1 second, 2 second, you hit it again. Okay, maybe lighter, okay, not as hard, and essentially your force is made of two pieces: initial hit, the latter hit. It's called double hit. Okay, and what you want to know, this is after half a second. Basically, plot the response of the function based on this information. You hit it once with the impulse value zero point 0.2, and you hit it again with an impulse value zero point 0.1. Okay, so another way of saying that is 0.2 delta t plus zero point 0.1 delta of t minus 0.5, minus half a second. Okay, now here is the drawing. This is the first hit. If you think about delta function as that, because remember, the delta function is 0 everywhere except at t equal to 0, but we can't draw something like that. So think about it. You can think about it always as a drawing like this, where the area under it is zero point 0.2. And the second hit at 0.5 second, the area under it is 0.1. Okay, now let's look at the initial hit. Now, first of all, we know what the response after the initial hit is. The response is going to be impulse response function h of t times the magnitude of the impulse times f hat. F hat, for that first hat, the area under that curve was zero point 0.2. So we do need omega n. We need zeta because in the expression for h, impulse response function, we have omega n, we have zeta, we have also omega d, right? So there's your omega d, initial hit. This is f hat. So we just literally write it down. X1 is equal to f hat times h of t. Just write everything down, and it's going to be this. Okay. Now, by the way, we are assuming that this whole thing starts from the rest condition. Okay, another block was not moving. Okay, it was at the initial position. Therefore, we don't have to worry about the initial conditions. They're both zero. Now, the second time we hit it is f hat is 0.1. Okay, but remember, nothing will happen. In other words, the solution we have is that first H that I got until I hit it again. I hit it again. So there is no contribution from this guy over here until half a second. Okay. So we want to know what is the contribution when we hit it the second time. Well, the second time means that this is shifted by the amount 0.5 seconds. So we know the impulse is appearing at tau equal to 0.5. So go back to the expression for impulse at tau, plug in your values, you get this. So here's what happened. Before half a second, the only thing that comes into the picture is that x1 because nothing, we haven't hit it yet. After after the uh, 0.5 second, we hit it, and the solution is whatever was there coming in plus the second piece. So it's going to be after 0.5 second, it is going to be this guy written plus the x2 that comes from the second hit. Okay. Let me also, if it's bothering you, let me also look at it like this. We have the mother of all equation equal to zero point 0.2 delta t plus zero point 0.1 delta t minus 0.5, right? And this is a linear equation. So we can think about the solution as being mother of all equation equal to 2 delta t. Get it? And the mother of all equation equal to 0.1 delta t. The solution is going to be the superposition of the two. But before 0.5 second, the second piece did not even exist. That's why it's only x1. But after you hit it the second time, the first solution is there. You have to add them up. Remember, you have to add x1 and x2. And therefore, you add x1 and x2 to get the response after 0.5 seconds. So here's what happened. Okay. So notice what happened is that this x1 is right here. This is x1. At this point, we hit it. Now, if we did not hit it, okay, it will be the continuation of that. But after we hit it, let me see for a second. Yeah, after we hit it, then x1 and x2 are added, and this dashed curve is actually x1 plus x2. Okay, this dashed curve is x1 plus x2. Okay. So solid line represents the response after the initial hit. Initial hit, that's it. The dashed line represents the total response after the second hit, the sum of x1 plus x2. And this is kind of misleading here. This actually should not be x2. This should, if it's a solid, if we are trying to represent, if we are trying to say what this dashed curve is x1 plus x2. So the dashed line represents the total response after the second hit, which means that it's going to be x1 plus x2. This is misleading the way it is written here. But go with the stuff on the left. This is where the second hit takes place. Notice that second hit imports an additional slope, an additional velocity, and that's why the velocity is discontinuous at this point. So the curve total response is up to this point. An initial velocity is given, another initial velocity is given, and that's why it becomes steeper, and then it goes all the way. Okay, so let's look at our second example. And this is the right hand side is given as delta t minus 4. And there is some initial conditions here, okay? So we're told that the initial conditions are x naught equal to 1 and v naught equal to minus 1. First of all, this is pretty much the same problem as the one that we just did. We have hit it twice. One at time t equal to 0 with an impulse of 1. The other one at time t equal to 4 or tau equal to 4 with an impulse of minus 1. It is exactly the same problem. The only difference is that on purpose, I didn't make both of these positive. Well, this is positive, this is negative. Okay. And I gave it some initial velocity. In the previous case, the block started from rest. So the way this is done in Inman is a little bit different from what I have done. So I like my solution better, and therefore I follow this. All right. First, look at the interval 0 to 4 before the second hit. This is the second hit. So essentially, it's the same problem as before. We have, if you look at the equation here, this is actually very immediately tells you what the mass is. M is equal to 1. But think about it as m equal to 1, and this is 2 xi omega n, and this is omega n squared. So instead of calling this thing m equal to 1, remember this coefficient in front of x dot, as long as the coefficient in front of x double dot is 1, this is called the standard equation and standard mother of all equation. So this is omega n squared. This coefficient that's multiplied by x of t is omega n squared, and this thing that's multiplied by x dot is 2 xi omega n. So out of this, we can find omega n and zeta. And damped natural frequency, you just go ahead and follow your formula. Now, for t less than 4, only the first impulse is active. We hit it once, okay? And the coefficient in front of this delta function is your f hat, which is +1. You can see that. So we just go ahead and plug in our solution in this, our numbers in this equation, and this is what we're going to get. This is the solution due to the impulse imparted on the mass does not include this initial condition. I have not used these two yet. Okay. All I said, suppose I have the mother of all equations equal to delta t. What is the solution? Well, it's going to be the impulse response function, which I wrote it here, right there, right there. This does not include that guy. Okay. Now, how do we find the solution? Let's, before we hit it the second time at 4 seconds, which includes those initial conditions. Well, uh, obviously, when we go with the initial conditions, you look at this, okay? And the solution to that, when you want to apply initial conditions, okay, let me put it a different way. To bring an initial condition to the equation, initial condition means x naught equal to 1 millimeter and x naught dot equal to -1. You're thinking about the homogeneous equation, right? Solution to this. The solution to the equation with a given right-hand side, which is delta of t, is made of two parts. The homogeneous part, which is this, plus the particular part that I just found for you. That the thing here, this is the particular solution when we have mother of all equation equal to delta t. And the solution, general solution, is made of two parts. The homogeneous part, which looks like that, the first 3 weeks of the course. And of course, you just go ahead and plug in your values. We don't know what A is. We don't know what phi is. A and phi come from the initial condition that we're given. And the solution in that time interval, 0 to 4, is made of the homogeneous one, which is right here, and the particular one that was the bottom of the very last slide. Okay, right there. We don't know what A and phi are. We get it based on the initial condition. Okay, and if you take this and apply those conditions to it, you're going to get these other conditions. You're going to get these two equations. You have to solve for A and phi. And if you do, you're going to get phi equal to minus pi over 3. Now remember, the phase angle for us is always between 0 and pi. The phase angle in this textbook and most textbook is between 0 and pi. So don't take that. This is the one in the fourth quadrant. Take the one in the second quadrant. So add pi to this. We went through this thing in the first 3 weeks. Okay, 2 pi over 3 and get the value of A. And there we are. For 0 to 4, there we are. This is the solution. Now, then we hit it the second time. But f hat is -1. So we can write the response due to this impulse, okay? By the way, this negative means that you hit the block in the other direction, in the negative direction, okay? Already you know what's going to happen, slow things down, right? So you go to the expression for impulse at a different time, tau equal to 4, tau equal to 4, this happens at tau equal to 4, f hat is -1, everything else we have, and you're going to get this. So here's what happened. After tau, after tau, t equal to 4, after t equal to 4, the solution is made of what we just got, do the second hit, plus the original one. You have to add to it the original one. So here's what happened. Before the second hit, there we are, the first 5 minutes of the problem. After the second hit, not only that, but also the thing that you just got a minute ago, previous slide. And notice that this is 4 equal to 4. You hit it with a hammer in the opposite direction, it slows it down. The velocity actually becomes, negative. The displacement, this is not the velocity, but you can see that this more negative, let's put it that way, because it was slowing down here, but then you hit it again, it even becomes more negative. So this, the dashed one is the solution to the problem. Up to t equal to 4, the dashed and red one are the same. After t equal to 4, you add these two up, whatever came from the first part, to the one that we just got, and we get this blue one. Okay. Yep. Now, the difference between the previous problem and this problem is that this was zero point 0.2 delta t plus that. That's why the velocity actually increased, became steeper. Here, there is a negative. That means we're slowing it down by hitting an impulse which is negative value in the other direction, and that's why there is a drop, further drop in the velocity. Okay. All right, so here we have something that looks familiar to us. We have a mass spring damper system. It's at rest. We're hitting it with a bullet of mass m naught, and the bullet gets embedded in it. In other words, it doesn't bounce out or whatever. It just gets perfectly, it's a perfectly uh, contact. Okay, perfectly inelastic collision. Let's put it like that. Now, what you want to know is what is the equation what is the mother of all equation for this problem when it gives you vibration of this, and also what is the natural frequency of the vibration. Okay, now when you look at this, when this gets embedded, obviously there are forces that are trying to push the bullet out, and there are forces that are trying to push the block M to the right. But these are the same forces, these are internal forces. In other words, in this particular problem, although there is an impact, but the, there are no external forces before, immediate, during the embedment of the bullet in that block. There are no external forces on the system. Okay, yes, later on, of course, you have force of the spring, force of the damper, but that is not during the initial embedding of the bullet in the block. So this is zero. So final momentum, m naught plus m of the system, m naught plus m, moving by the amount, velocity which we call x naught zero, minus the initial momentum, only the bulleted momentum, equal to zero. And that means the mother of all equation is the total mass of the block and the bullet, x double dot plus cx dot plus kx equal to zero. Initial condition, displacement is zero. Initial velocity, we just got it out of that. So notice that we didn't have to do the impulse response of the system. There was no external impulse here. The impulse is due to external forces. Well, let me restate what I meant. There are no impulses due to external forces because there are no external forces on the system as a whole during that interaction. Okay, and obviously the natural frequency is going to be the ratio of k over m naught plus m. Here's another problem. We have a gadget which is falling off the sky. Okay, we can imagine this is a camcorder, this is a suitcase or whatever. Okay, and this will hit the ground after traveling a distance h, and there is no rebounding, so this doesn't bounce up again, it just sticks to the ground. First of all, we write the mathematical model of the vibration of this problem, because obviously when it hits it, this thing hits the ground, the mass starts going crazy up and down. You want to write the equation of motion for that, and find the maximum acceleration experienced by this mass. Okay, what is the maximum acceleration experienced by the mass? Now, there is an impulse imparted on the mass here. Okay, so the mass does feel an impulsive force, and this is why it actually starts moving up and down. Let me take a short break here. Okay, so this package is dropped, and it sticks to the ground. It doesn't bounce back. Now there is an impulse applied to that mass, and you will see that in a second. Where is that coming from? First of all, we can use the conservation of well, let's say a work energy equation to find what is the velocity on the ground. So initial kinetic energy, let's say up here from that height, initial kinetic energy is zero because it's released from that height, and the work done is going to be the mg times this height, okay? And the kinetic energy at the very bottom is 1/2 mv squared, and you equate these, and you're going to get the velocity of the or the speed of the this package when it hits the ground. So this is basically the work energy equation, and you're going to get the velocity when it hits the ground. There is an impulse that must have been applied to this block. Okay, so here's the situation. This is the equation. This is the equation. Okay, notice that I'm not using anything in particular as far as the what is the value of the impulse, etc. So the velocity suddenly essentially changes with respect to the base, and therefore we know how to handle a problem like that. Okay, there is no force. There is no force applied except for that except for what is coming from the initial additional initial velocity that's imposed. Okay. Now, if in here, if you plug in your v naught equal to square root of 2gh, and I mean x naught is zero, immediately when x naught is zero, this whole thing tan inverse of zero is zero, so phi is becoming zero. So we know what a is. So this is actually right there. Okay, and uh, but when you think about it, by the way, this is that impulse response function. Okay, so when you look at this expression, you get the feeling what was the impulse applied to that mass. So remember, for the for this is playing the role of your h, except that there is an m missing. Okay, there is an m missing here. So if you put an m here and an m on the top, this becomes your impulse response function, your h of t, and this becomes your f hat, m square root of 2gh becomes your f hat. Okay. Now, the maximum acceleration is, if you look at the maximum acceleration is it's the maximum of x double dot. Okay, you can plot this if you want and find out what is the maximum x double dot, or you can differentiate it to find the maximum of x double dot. You have to differentiate this thing 3 times set it equal to 0. But if you have your x, it's right here, and you plot it analytically, you plot it, you're going to get the maximum x double dot. Now just look at this. This is your x. X double dot is going to be some ugly expression, and plot it, find out what the value is. Here is another problem that I want to do, and that is we have a wing which is going to be modeled as a cantilever beam. There is a missile that's going to be fired. Some information is given to you about the material. This is aluminum. This wing is going to be modeled with a cantilever beam with Young's modulus being of the aluminum. Some information about the length, 4 meter length, damping experimentally measured probably, and the mass of this wing is 1,000 kilogram, and the missile fires, okay, and imparts a force of 1,000 Newton on the wing. When the missile fires, it remember it pushes the wing back, right? Pushes the wing back, and for a very short period of time, that force is acting, which 0.2 seconds. So we're going to solve this thing as an impulse response problem. So an impulsive force on the wing is applied, and we have the information, and we can solve the problem and get the response of the wing. In other words, the displacement or the displacement, horizontal displacement of the wing as a function of time. So let's see now. Uh, you know, pretend that the actual there was a sensor installed on the wing, and it measured the, for example, the force imparted by the missile, and it looks like that. So we're going to approximate this. This is an impulsive force. We're going to approximate it with an average value of 1,000 Newton over a 0.02 second. So the impulse value of the impulse is going to be 1,000 here, 1,000 newtons times 0.02, which is going to give you 20 newton second, right? Yeah. Now we need a bunch of things here. The stiffness, the K of this single degree of freedom system. So we're going to model this complicated problem as a single degree of freedom system, which is a disaster, right? But that's what you can do. That's the whole point of modeling some complicated with a single degree of freedom system so that you can get some very quick answer. And if you want to refine it, then you have to go and do other things, finite element studies, etc., etc. So here is the K. The mass of the wing was given to you. I think it says 1,000 kilograms, if I'm not mistaken. You're right there, and you're going to get natural frequency, and you get a damped natural frequency, and then you write the impulse response function. So F hat is this area, which is uh, F hat is 20, right? 20, and if you plug everything here, you're going to get this. Okay. Yep. Actually, what I've done here also plotted this response for you. And this is because there's damping involved. Obviously, the oscillation of the tip deflection of the wing is going to die down. But I've also plotted over this very short period of time, so you can see that it's sinusoidal, but the amplitude is decreasing. You can already see that it's smaller here than than what it started with previous hump. The last problem of the day. These things can be done with for torque problems. So we have basically a setup like that. This is a torsional vibration, right? So the top of the bar is clamped, and there is a disc here, and there's a force, a very short duration force is applied here. Therefore, it gives you a very short duration moment. Okay, and we want to find the angular deflection. First of all, solve it and find the angular deflection by how much does this thing rotate. Think about it like that. Angular deflection means rotation after 1 second. So we are given the properties of this, what this is made of. All these are all of steel, and the impulse is going to be in terms of moment. It's going to be a force times uh, the duration, 0.005 times this radius, okay? Because moment is force times moment arm. So it's going to be force times the moment arm, which is half of that, this radius, times the duration. It's going to be uh, the, the impulse, moment impulse in the appropriate unit. Now, we can use exactly the same formulas. In other words, the response of the oh, not the wing was the previous problem. The response of the structure, which is rotation or torsional vibration of this, is going to be just like that, except that things have to be appropriately interpreted. So this F hat is this number, okay, it's actually M hat, okay? And this is also the same thing, except that we don't have M, we have J. Now, I need the J and stuff I have done using MathCAD, because you need the K also, right? Let's go back here. Let's go for a second. To find omega n, you need the mass of this, we're going to ignore the mass of the bar. You need the mass of this, you're given density and all these things. And then once you find the mass, you're going to need the stiffness of that guy, a bar on the torsion. It's a torsional stiffness, basically. So these are things that we did in slide 15, lecture 4. All the formulas were here. For example, KT, the KT, which is a torsional stiffness of this bar, is through that formula. Okay, so here's the mother of all equation. Okay, this is all from slide 15, lecture 4. Now, what I've done is done a math calculation. So all these things, these are geometrical effects, the diameter of the shaft, the radius of the disc, and the length of the shaft, and the height of the disc, because these we need for finding masses and things like that. This is the material properties. Remember, you need the G, which is shear modulus, which is given in terms of that, and your force was 10,000 Newton over that period of time. You have to multiply by the radius, okay? And then just the mass of the disk, you know how to do that, the volume times the density. We're going to ignore the mass of this shaft, okay? But we need the mass of the disk because we're going to need it in J. Remember, this is a disk of mass M now, which we calculate from here, and it's going to be 1/2 mr squared. This is stuff from well, actually from strength of material or from deformable bodies or from stress analysis. And we find the torsional stiffness of that bar, okay? Remember, we have to find the pi d to the 4/32. And these are the natural frequencies. I put the K in here, I put the J in there, and I get this is the natural frequency of the oscillation of this disk. And here is your impulse response function. Impulse response function. Remember, we ignored damping here. I've ignored damping. That's why things are a little bit easier. There is no e to the minus psi zeta omega n anymore, and there's no omega d because we have ignored damping. And the response of the system is going to be this. This is your impulse response times m hat. Now I can't write m hat here, so I wrote m hat like that. M hat was impulse, in other words, this thing right there. And then plug in theta equal to, or t equal to 1 second. We wanted to know what the angular position is after 1 second. It's that many radian, which is approximately 1.57 seconds. So that's a lot of stuff. I understand that, but this is why there is a video there. If I said something that doesn't make sense, you stop the video, think about it, come back and talk to me, because occasionally I say things I don't mean it. And now you have everything in front of you. The ball is in your court. Good luck. There's the curve, by the way, sinusoidal. You know that. There's no damping, constant amplitude. Good luck.